Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module Chemical Methods for Deposition of Thin Films. The qualitative study of preparation of thin films by electroplating, vapor phase growth and anodization, which is from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we are going to learn about the chemical deposition techniques of various kinds, the advantages of chemical techniques over the physical techniques. Then we are going to discuss the chemical techniques like LPCVD and PCVD and their advantages over the conventional CVD techniques. Then next we will study the sol gel technique of the deposition of thin film explained by a step-by-step process and also its economic importance. Chemical deposition process or the CSD technique, or we can call as sol gel processing, is the convenient and versatile method to synthesize ceramics, glass materials in a wide variety of forms such as powders, thin film coatings, microporous inorganic membranes, fibers, monoliths, and porous aerogel materials. CSD technique involves the preparation of homogeneous solution of desired compounds either by dissolving metal organic or inorganic salts in a desired polar or non-polar solvent. Starting chemicals are usually complex compounds of the relevant metal ions acting as solutes and are called as precursors. Thereafter, the prepared homogeneous solution was treated with suitable stabilizers for aging and capping agents to obtain the desired controlled shape. In CSD technique, various combinations of precursor solvents and stabilizers have been employed in the production of thin films. Their unique properties and reactions affect the preparation process and determine the final product. Therefore, essential features of precursor and solvent are need to be highlighted. Ideal features of compound to be used as precursors are: number 1, high metal content to minimize the volume change during the transformation from metal organic solution to inorganic film. Secondly, high solubility in the common solvent with other starting compounds. Number 3, it should be chemically compatible with other compounds accordance to the formulation. Lastly, or number 4, is the ideal precursor should be cost effective to reproduce as the capital equipment requirements is small with no vacuum systems requirement. The cost of precursors should not change this advantage. It should not thermally decompose without evaporating, melting, or leaving a carbon deposit. So the ideal features for a compound to be used as precursor are: number 1, it has a high metal content, it should be highly soluble, it should be chemically compatible, and the fourth one is the cost effective. Now after seeing the features of the ideal compound to be as an ideal precursor, let's see the ideal features for solvent. For an ideal solvent, high vaporization rates should be there so that it evaporates quickly at lower temperature as possible, where vaporization depends on vapor pressure and also interaction between solvent and solute. Therefore, careful selection of a solvent is necessary in order to get a solution with high concentration of necessary components, proper viscosity and surface tension. Now, depending on the nature of the precursors, there are several preparation techniques available for the synthesis of materials by CSD technique. Some of the techniques are listed below. The first CSD technique that we are going to discuss is all alkoxide method. Generally, alkoxide of each metal with desired composition are dissolved in an alcohol solvent. Thereafter, addition of water to alkoxide solution results in hydrolysis, which is followed by condensation, network formation, and the eventual formation of polymeric gel or sol. Nowadays, advanced ceramics are multi-component materials having two or more types of metal cations in the same lattice. Since alkoxide precursors are mixed at the molecular level in the solution in the bottom to top approach, therefore a high degree of homogeneity is expected. However, unequal hydrolysis and condensation rates of the used metal alkoxides leads to major problem in forming homogeneous multi-component solution. Also, it results in phase separation during hydrolysis or thermal treatment, leading to higher crystallization temperatures or even undesired crystalline phases. Therefore, the formations of multi-component alkoxides are hard to achieve, thus forcing to choose an alternative method for the synthesis of multi-component materials. The next method which we are going to study is the modified alkoxide salt method. The alkoxide salt approach can overcome the aforementioned problems with all alkoxide method. Need to form the multi-component materials with desired composition. The term salt for the desired process basically refers to carboxylates, nitrates, sulfates, carbonates, chlorides and hydroxides. The alkoxides and the carboxylates fall in the group of organic derivatives of metals with metal oxygen carbon bonds, while nitrates, sulfates, carbonates and chlorides comes in the category of inorganic derivative of metals. Certain species like carboxylate anions, which we can write as RCOO-, nitrates, which are denoted by NO3-, etc., are found to be a versatile ligands capable of binding the metal in chelating or bridging modes. The metal carboxylates have the important feature of forming metal-metal bond. A metal acetate or nitrates works for most metals and are active source of metal oxide. The choice of solvent is very important in alkoxide salt approach as its influence can be multiple. It can stabilize intermediates and thus modify the reactions. The utilization of different derivatives of alcohol as solvents help in further formation of the reactive species. The main advantage of the modified alkoxide salt approach is the formation of comparatively non-reactive side product in comparison to all alkoxide approach. In all acetate alkoxide sol, either the choice of carboxylate salt or the solutes or the alkoxide alcohol, that is the solvents, holds the bridging position and binds different metals together. These reactions are further controlled by adding complex agents known as stabilizers that react with metal precursors at a molecular level, giving rise to a new molecular precursor of different structure, reactivity, and functionality. The prepared solutions using above mentioned methods can be used in various ways for the preparation of thin film structure. To obtain the layered thin film structures, coating of prepared homogeneous solution on a substrate can be done using the spin coating or dip coating techniques to obtain an inorganic oxide thin film, whereas the post-deposition thermal treatment is required for the crystallization of as deposited amorphous films. Now in the dip coating technique, the uniformity and the thickness of the film is controlled by optimization of various parameters like rate at which the film is pulled out of the gel, or the time for which the substrate was kept in the solution, and viscosity of the solution. While in the case of spin coating technique, the uniformity and thickness of the film are controlled by the spinning rate, the time, and the viscosity of the sole. However, sol gel derived powders can also be obtained further either by precipitation or high temperature treatment, which can be used in the formation of thick disc and pellets. These obtained pellets can be further utilized as targets for the deposition of thin films using PLD and sputtering. The given figure shows the schematic of the chemical route technique, in which we can see that there are two precursors, precursor A and precursor B. They are dissolved in the solvent, which results in the homogeneous solution. Now this homogeneous solution is converted into the thin film form by either the spin coating or the dip coating method, in which we put the drop over the substrate and it gets spinned by the spin coater machine, or by dipping the substrate into the solution and taking it out. After getting the film on the substrate, we get the final form of the crystalline thin film by drying or by annealing the amorphous obtained thin film. The next technique that we are going to study is the spin coating. Preparation of a highly cross-linked solid thin film onto the substrate can be achieved by means of hydrolysis and condensation of the molecular precursor using the spin coating technique. In the spin coating technique, the substrate is placed on the chuck table and held by the vacuum of the order of 10 raised to the power minus 2 millitorr while rotating. Once the substrate is fixed on the chuck, the filtered precursor solution is drop casted on the substrate using a pipette in measured quantity and allowed to spin at a particular rotations per minute or RPM in spin coater. Typical spinning speed is ranging from 500 to 6000 RPM, depending on the properties of the fluid as well as the substrate. To achieve a required thickness of film along with uniformity, the combination of spin speed and time are selected and optimized. In the spin-up stage, the liquid flows radially outwards by means of centrifugal force acting outwards, giving rise to the formation of uniform thin film. In general, higher spin speeds and longer spin times are observed to form a thinner films. In spin coating process, it involves a large number of variables that tend to cancel and average out during the spin process, and it is best to allow sufficient time for this to occur. A separate drying step is sometimes required after the high speed spin step to further dry the film. This can be advantageous for the thick films since long drying times may be necessary to increase the physical stability of the film before handling. A firing process is necessary to remove the residual organic solvents and organic groups in the deposited film to convert the organic precursor film into an inorganic film. Because of the large volume shrinkage accompanying the densification process during firing, cracking of the films is a serious problem. To prevent cracking, a multi-stage deposition process is adopted. The spin-on layers was pyrolyzed in air at 300 degrees Celsius for 5 minutes on a preheated hot plate. Thicker films were prepared by repeating the deposition and pyrolization cycle. Multiple coatings were required to achieve a required thickness. Finally, a post-deposition heat treatment is provided in air required for further densification, grain growth, and to obtain highly crystalline structure of thin films. So the figure given here shows the process which occurs during the spin coating technique. First process is the deposition, then the spinning, then after getting the film on the substrate, we dry that film. After that, the solvent gets evaporated and we get the desired crystalline film after giving the required heat treatment. Applications. Sol gel derived materials have various applications in optics, electronics, biosensors, etc. They are used in ceramics manufacturing processes as well. Then thirdly, products manufactured with this process include various ceramic membranes for microfiltration, ultrafiltration, and reverse osmosis. The advantages of CSD technique over the other deposition techniques are: number one, the CSD technique provides excellent adhesion between the substrate and the top coat. Secondly, there is no deterioration of substrate surface. Number three, it helps in obtaining the desired shapes of materials into complex geometries. Number four, high purity products can be obtained by choosing the high purity precursors. Number five, low temperature sintering capability, which is usually between 200 to 600 degrees Celsius. And lastly, CSD technique is the simple, economic, and effective method to produce high quality thin film coatings. Now, after seeing so many advantages of CSD technique, we should also know about the disadvantages of CSD technique, which are as: number one, it is very difficult to control the porosity of materials by using this technique. Number two, weak bonding, lower wear resistance, and high permeability is there. Number three, limit of the maximum coating thickness, as high value of thickness may result in cracking of the films. That means we can only achieve a certain level of thickness using CSD technique, and above which film starts cracking. And lastly, CSD technique is not suitable for bulk production. The next technique is electroplating. Electroplating is the application of a metal coating to a metallic or other conducting surface by an electrochemical process. Electroplating is both an art and a science. Although based on several technologies and sciences, including chemistry, physical, electrical, metallurgy, it retains in some ways the aspects of an art. In fact, of course, all the sciences have elements of art which can be learnt only by experience. All the reading of textbooks on chemistry will not produce a chemist. So, no text on electroplating will actually produce an expert electroplater, and there is no substitute for experience and what is somewhat inelegantly termed know-how. So, given figure here shows the electroplating mechanism, in which we can see there are two electrodes, one is the cathode, one is the anode, then there is the solution, and there is a battery connected between the two electrodes. In our case, the solution is the copper sulfate, anode is the copper rod, and cathode is the silver. So it is actually a copper plating example. The next method is the plasma enhanced chemical vapor deposition, which is called as PECVD. PECVD is the CVD process which uses plasma or the cold plasma to deposit thin films from a gas state to a solid state on a substrate. The reaction involved in this process occurs after the creation of plasma of the reacting gases. This plasma is created by RF, that is the AC frequency, or the DC discharge between two electrodes. The space between the electrodes is filled with the reacting gases. Through this process, we can deposit films on substrates at lower temperatures than that of standard CVD process. Let's discuss about the underlying process about the plasma. Plasma is that state of gas in which a significant percentage of atoms or molecules are ionized. Plasmas with low fractional ionization are important or are of great use in the material processing because electrons in such plasma are very light as compared to atoms and molecules, such that the energy exchange between the electron and the neutral gas being used for the creation of plasma is very insignificant. The plasma used for processing is operated at pressures between millitorr to few torr. Since the electrons are very light, so they could be maintained at a very high equivalent temperatures, equivalent to several electron volts average energy, whereas the neutral atoms remain at the ambient temperature. These highly energetic electrons are efficient to induce many processes that would otherwise be very difficult to process at low temperatures, such as dissociation of precursor molecules and the creation of huge amount of free radicals. Another benefit of deposition within a discharge arises from the fact that electrons are more mobile than ions. Due to this, plasma becomes the most positive among the things it is in contact with. The difference of the voltage between plasma and the object in its contacts generally occurs across a thin sheath region. Ionized atoms or molecules diffuse to the edge of the sheath region. They feel an electrostatic force and are accelerated towards the neighboring surface. Chemical deposition process. Thus, all the surfaces which are exposed to the plasma get energetic ion bombardment. The potential across the sheath that surrounds an electrically isolated object is around 10 to 20 volts, but much higher sheath potentials can be achieved by adjustments in reactor geometry and configuration. Thus, films can be exposed to energetic ion beam bombardment during deposition. The bombardment often leads to increase in density of the film and help to remove contamination, thus improving film's electrical and mechanical properties. When high density plasma is used, the ion density is high enough such that significant sputtering of the deposited film occurs. This sputtering can be used to help in making the film plane and fill troughs and holes. There are two parallel electrodes in the system. The first one is the grounded electrode and the second one is the RF energized electrode. This capacitive coupling between the electrodes excites the reactant gases into plasma, which then induces a chemical reaction and results in the reaction product, which is then deposited at the substrate. The substrate is placed at the grounded electrode is generally heated to 250 degrees Celsius to 350 degrees Celsius, depending on the film that needs to be deposited. In comparison to the CVD or the chemical vapor deposition, it requires 600 degrees Celsius to 800 degrees Celsius. The lower temperature requirement is very essential in some cases where higher temperatures, such as in CVD, may damage the device being fabricated. Applications. It has many important applications in material deposition and it has been used commercially to deposit following films. Number 1, silicon oxide, silicon nitride, for a wide range of applications including photonics, structures, passivation, hard mask, etc. Second is amorphous silicon. Third one is silicon carbide. And lastly, the diamond-like carbon. The advantages of chemical deposition process. Number 1, low operating temperature. Number 2, uniform coating of different shapes. Number 3, good step coverage. Number 4, high packing density. Number 5, there is a less stress. However, the following drawbacks are also there. Number 1, precursors are toxic and so are the byproducts. So the chemical deposition process includes the toxicity. Number 2, equipment is not economical. Number 3, the capacity of producing the products is limited. Number 4, contamination can occur from precursor and carrier molecules. So students, let us summarize what we have learned in this module. First of all, we have learned about the chemical deposition techniques of various kinds. Then secondly, we studied the advantages of chemical techniques over the physical techniques. Thirdly, we discussed the chemical techniques like PCVD, LPCVD and their advantages over the conventional CVD techniques. Fourthly, we realized the importance of ALD technique in the deposition of thin films with atomically controlled thickness. Lastly, we discussed the sol gel technique explained in detail by step-by-step process and its economic importance has also been described. Thank you.